Welcome to this documentary-style explainer. Today, we're diving into one of the absolute most fascinating, mind-bending historical mysteries in all of physics. We're talking about the bizarre world of quantum entanglement. We are going to unpack a decades-long, intense debate between two of the greatest minds in scientific history. And don't worry, we're going to tackle this by focusing directly on the core concepts, so we won't get bogged down in any complex math.
Okay, to start us off, we actually have to ask a question that sounds, well, it sounds like a late-night philosophical joke, but it was a deeply serious challenge at the time. Is the moon still there when nobody's looking at it? You see, Albert Einstein's biggest objection to the brand new science of quantum mechanics wasn't about the math at all. The math actually worked perfectly. His issue was with this embarrassingly simple, profound question about the very nature of reality. Quantum mechanics seemed to suggest the moon might literally not be there until you check. And Einstein? He thought that was totally absurd.
All right, Section 1. Einstein's quantum discomfort. So to really grasp this conflict, we've got to rewind back to the 1920s when physics was going through a massive revolution. A totally new concept had just emerged called the quantum wave function. It basically suggested that a particle's properties, stuff like its location or its speed, don't actually exist in any definite state until someone measures them. Before you measure, they're just a cloud of probabilities.
Now, this idea deeply unsettled Einstein because it completely threatened two of his most sacred rules of physics. The first rule is realism. This is just the idea that physical systems have definite properties that exist completely independently of whether anyone is measuring them. Basically, a particle has a position whether a scientist is in the room or not. The second rule is locality, which comes straight from Einstein's own theory of relativity. It states that no influence, signal, or information can ever travel faster than the speed of light. Cause has to absolutely precede effect, always. So this created a massive ideological split in the physics community. On one side, you've got Einstein championing what we call local realism. He firmly believed that because quantum mechanics only gave us probabilities, it had to be an incomplete statistical shortcut. It was a useful tool, sure, but it was missing the true, deeper description of reality. On the flip side was physicist Niels Bohr and the Copenhagen interpretation of quantum mechanics. Bohr pushed back, insisting that the theory wasn't incomplete at all. Instead, he argued that the universe had simply outgrown our classical everyday intuition. Reality itself was inherently probabilistic.
Which brings us right into Section 2, the EPR reality trap. Fast forward to 1935, in Princeton, New Jersey. Einstein, along with two collaborators, Boris Podolsky and Nathan Rosen, set up a remarkably clever philosophical trap to prove quantum mechanics was fundamentally incomplete. Now, what's really elegant about their argument, this short, 4-page paper, is that they proposed a really modest, hard-to-argue-with criterion for reality. They basically said, look, if you can predict a property of a system for certain without in any way touching or disturbing that system, well, then that property has to be an element of physical reality. It must be tangibly real, whether quantum theory wants to admit it or not.
To prove this point, they came up with a brilliantly simple thought experiment. Step 1. Imagine two particles interact and then separate by some massive distance, let's say 4 light-years apart. Quantum mechanics says these particles are now entangled or linked. Step 2. You measure the spin on particle A right here on Earth, and let's say it comes up as up. Step 3. According to quantum mechanics, particle B, which is 4 light-years away, instantly snaps into a down state. This happens at the exact same instant. There is literally zero time for a signal to cross the vast emptiness between them.
And boom, here's exactly how the trap closes. By EPR's own logic, since we can now predict particle B's state with absolute certainty without ever touching it, that property had to have already been real, definite, and waiting before we even measured particle A. Einstein argued this instant correlation was proof that the particles must have carried hidden, local instruction cards with them from the very moment they separated. Why? Because the only other alternative, some kind of signal traveling faster than light, was literally impossible.
Now, you might be wondering how the scientific community reacted. Well, it brilliantly illustrates a complete stalemate. For 30 whole years, this debate was just frozen in time. Everyday physics marched right forward, racking up massive triumphs in quantum electrodynamics and electronics, while almost everyone just treated the Einstein-Bohr debate as an untestable, private philosophical quirk. It was basically brushed off as an argument over semantics, not real science.
But of course, that stalemate couldn't last forever. Section 3. John Bell's Genius Test.
In 1964, a somewhat obscure physicist named John Stuart Bell finally figured out a way to turn this 30-year-old philosophical cold case into an actual, testable mathematical formula. Bell actually built a mathematical inequality that directly tested Einstein's whole idea of instruction cards. His stroke of genius was to propose measuring these entangled particles along independently random angles. Basically, if the particles truly just had hidden, pre-existing properties loaded into them at birth, there was a strict, mathematical ceiling to how often their measurements could correlate when tested randomly. But if quantum mechanics was right, it would shatter that mathematical ceiling completely.
Let's move to Section 4, Testing Reality in Labs. So, we're stepping out of pure theory now to see how this builds into physical laboratory experiments that literally put reality on trial. Bell gave us the math, now the physicists just needed to build the machines. When you trace this timeline, it's just incredible. From the original 1935 EPR paper, it took 29 long years for Bell's theorem to even emerge. Then, 47 years after the paper in the early 1980s, Alain Aspect ran these truly groundbreaking experiments over in Paris. Aspect built a system that switched the measurement angles super rapidly while the photons were literally already in flight. This closed the loophole that a slower-than-light signal could somehow fake the results. And all of this work finally culminated, 87 years later, in the 2022 Nobel Prize in Physics for researchers John Clauser, Alain Aspect, and Anton Zillinger.
Section 5. What it all means. So, what was the final verdict after all that? Well, after 50 years of rigorous testing on every continent, and eventually even from space satellites, the results were absolutely conclusive. Nature firmly, unambiguously rejected Einstein's strict local realism. The correlations between entangled particles were just way too strong to be explained by any pre-existing hidden instruction cards. But hold on, because this leaves us with a massive, lingering question. If Einstein's hidden properties are out, and these particles really do affect each other instantly across light years, did we just break the speed of light? Like, can we use this to send messages instantly across the galaxy?
So the crucial point here is no. We absolutely did not break the cosmic speed limit. This is governed by something called the no communication theorem. It basically proves that while entanglement is 100% real and particles do share these instant correlations, no usable information, no causal signal ever actually travels faster than light. You get random correlations, sure, but you cannot use them to build a faster-than-light telephone. Relativity survives completely intact.
So what does break? Well, it's simply our comfortable, everyday assumption that separated objects must have fully independent properties. The experiments proved the mathematics of what happens, but physicists today still intensely debate the underlying reality. They're totally split between competing interpretations. Is it the Copenhagen shut up and calculate model? Is it the many worlds interpretation? Or maybe relational quantum mechanics? The equations work flawlessly, but the actual story underneath them, still a profound mystery. And despite that deep philosophical mystery, this weird theoretical phenomenon is literally driving cutting-edge technology today. We're using entanglement right now for quantum computing, which allows for exponentially faster calculations. We use it for quantum key distribution, creating this amazing tamper-proof cryptography where just eavesdropping mathematically destroys the link. And we even use it for quantum teleportation, transferring precise quantum states across vast distances. But keep in mind, every single one of these mind-blowing practical uses still fundamentally requires a slower-than-light classical communication channel to actually work.
Ultimately, entanglement forces us to totally reconsider the universe's basic building blocks. We have to move away from this ancient, comfortable idea of atoms as tiny, independent billiard balls bouncing around. Instead, we're moving toward a modern understanding of a reality that's defined fundamentally by relationships and non-separable correlations. It turns out, the universe is far more deeply interconnected than we ever realized. Which leaves us with this final crazy thought to ponder. Einstein got half of what he wanted, right? No signals can outrun light. But the universe was apparently never required to guarantee that the moon is always there when nobody's looking. So if the universe isn't made of independent local objects, are we just quantum correlations all the way down? It's pretty wild that a question that started as a philosophical argument over breakfast turned into a mathematical theorem and ended up redefining reality itself. Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you next time.